this video has sound. Hopefully everybody can hear it, or otherwise they're watching me point at this sign and hopefully getting their sound up and going. So this is a lesson on Chapter 12, Section 1 out of the Chapter 12 Geometry Study Guide. Some preliminary vocabulary in this section is necessary. Basically what we're going to be looking at are something called solids. Basically that's a three-dimensional object. So here's some examples of what solids look like a can of soup or an ice cream cone type shape, or a ball, pyramid, stuff like that. So a polyhedron is basically a three-dimensional solid where all the sides are flat surfaces. Those surfaces are called faces. I basically like to call them the walls of the side of the room. So if you think of a three-dimensional object as a living space, anything where you have a floor, ceiling, or sides, I call those walls. And usually they're on the sides, not the top and the bottom. We have other names for that. For example, the base is the name for the bottom surface on your three-dimensional object. A vertex is a point where any three corners come together, or any three edges meet. A point where three edges meet, or I just like to call it a corner on your shape, more simply put. And then an edge is basically that. An edge is an edge. This is one of the edges on my calculator. Here's another edge right here. It's basically here's an edge on my pyramid. Here's another edge right here. This is an edge here. So I think that's pretty much granted that you would know what an edge is. A regular polygon simply means that all the faces are congruent. Like on a Rubik's Cube or on a rolling die. All the faces are the same side because they're all squares, or the same size and shape. So when all the faces are congruent on a three-dimensional object, then that's called a regular polyhedron. Platonic solids and convex polyhedron, you don't really need to know what those are, but you do need to know what a cross section is. A cross section is basically what happens when you cut something through the center. So if you take a whole loaf of bread that's not sliced and you slice the piece of bread, and then you look at what it looks like when you tip it open and look at that sliced face, that's a cross section. It would be like taking an orange and cutting it in half and then looking at what the orange looks like on that side where you've sliced it. That's a cross section. So it's basically a flat surface created by slicing through a three-dimensional object. Okay, we'll talk about that a little bit later in the lesson, but basically let's just talk a little bit more about specific solids, because just like two-dimensional shapes have names, like rectangle, square, triangle, circle, you know, kite, rhombus, trapezoid, all that, Three-dimensional shapes also have names, and here are some of them. A cylinder basically looks like a soup can shape. It's got circles on the top and the bottom, and then a wraparound surface connecting the two. A cone is a cone. We tend to, in math, we tend to look at cones upside down from an ice cream cone. Usually you hold the ice cream cone with the vertex down, but in math we tend to put the vertex at the top. A pyramid often has a square base, but it could have a different size shape base. It could have a pentagon base or a hexagon base or a triangle base. And then it has sides that kind of connect together at the top to form a vertex. And a sphere is a perfect round three-dimensional shape. Now, tell whether the solid is a polyhedron. If it is, name the polyhedron and find the number of faces, vertices, and edges. So basically a polyhedron is a 3D solid in which all the sides are flat. That was the first definition over here, right? So all the walls, the ceiling, the floor, and all the surfaces all the way around have to be flat. So does A have all flat surfaces? Seems to me the three walls are flat, the bottom is flat, they're all triangles, so this one's a yes. Naming it is not something we're going to quiz you on. This is technically a tetrahedron because it has four faces, but you don't have to know that, so I'm not going to write it. Does this three-dimensional object have all flat walls and surfaces? Yes. So that is also a polyhedron. Does this one have all flat, meaning, you know, like a piece of paper or a tabletop surface? No. This top part is rounded, so that is not a flat surface. So this would be a no. That because of the rounded nature of the top part of this object, this third example C is not a polyhedron. How about these? Number 1, well, certainly not. It's got rounded parts to it, so that's not a polyhedron. Number 2, all flat surfaces? Yes, so that's a polyhedron. And number 3, no, it's got a rounded surface here on the left side, so no. Okay, now most of this quiz is going to be on this concept here. It's called Euler's theorem because the man that discovered it was named Euler. That was his last name. The number of faces, remember that's the walls, or how many surfaces are on the outside of the shape, and vertices, that's the corners, right? On this particular shape you have 8 corners, 1, 2, 3, 4 on the bottom and 1, 2, 3, 4 on the top. And edges, that's these things here. There's 1, 2, 3, 4, 5, 6. There's up to 12. Well, there's 12 on this particular shape. So he said that he found a relationship when you start kind of comparing the numbers here. He said that if you add up the number of faces plus the number of vertices, that equals the number of edges plus 2 every time for any type of polyhedron. It doesn't have to be a regular polyhedron. As long as it's a shape or it's a three-dimensional object and all the faces are flat surfaces, this theorem works. So for example, here's a three-dimensional object with all flat surfaces. It has 8 faces, 1 in the front, 1 in the back, 1 on the top, 1 on the bottom, 2 on this side and 2 on that side. That's 8. How many corners does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 vertices. And it has 18 edges if you count them all up. So 8 faces plus 12 vertices is 20. So is it true that 18 plus 2 is 20? Yes. Euler's theorem is right again. So we can apply Euler's theorem if there's something that's unknown. For example, if we don't know how many faces this object has, but we know that it's a polyhedron, and we know that the number of vertices is 8 and the number of edges is 12. So basically, If you take the number of faces, add it to the number of vertices, you should always get the number of edges plus 2. So number of faces we don't know, we'll call that n, because they called it n here. Vertices is 8, and edges is 12. So basically, if n plus 8 equals 14, we can solve this like an equation, or we could just do it with mental math. Either way, solving in our head or solving on the page like I'm doing now, you should get the number of faces to be 6. Here they don't know the number of edges, so if the number of faces plus the number of vertices equals the number of edges plus 2, we'd have 5 plus 6 equals n plus 2, so that's 11 equals n plus 2. Obviously this number would have to be 9 because 9 plus 2 equals 11. So here the number of edges is 9. And then finally, number of faces plus the number of vertices equals edges plus 2. So we would have 8 plus, we don't know the number of vertices, so we'll put n there. Edges is 18. So 8 plus what number equals 20? Well, that would be 12. The last two examples, they want us to count everything. Count faces, count vertices, count edges. For number 10, the number of faces, I have front, back, the two sides of the roof basically, and then the bottom. So that would be 5. Vertices is how many corners it has. 1, 2, 3, 4, 5, 6 corners. And edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. So they want us to check our answers by using Euler's theorem. So if faces plus vertices equals edges plus 2, I get 5 plus 6 equals 9 plus 2, 11 equals 11. Yep. Number 11. Number of faces, I have front, back, top, bottom, side, and side, so that's 6. Vertices is the number of corners, 1, 2, 3, 4, 5, 6, 7, 8. Edges, if I count them all, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 14 does equal 14, so Euler's theorem works again. Should always work as long as you have a three-dimensional object where all the faces are flat surfaces, not curved. So let's see what we have on this number 12. Example, faces 1, 2, 3, 4, 5, 6 for the bottom. So all the 5 walls up here and then the bottom makes 6 faces. Vertices are corners 1, 2, 3, 4, 5, 6. And edges we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yes, 12 equals 12. Euler's theorem is correct again. Now the next page has to do with that last definition that I talked about on our first page of concepts. A cross section, remember I talked about if you cut a loaf of bread, that's one full chunk of bread in half, and then you look at that surface that you created with that slice, that's a cross section. Or if you take an orange or an apple or something and cut it in half and then just look at that surface that you created when you sliced through it, that's called a cross section. So page 10 here is asking you what shape do you make when you cut through the object. So do you see this plane here? That's where they're cutting through the object with. So if I take this ball shape and I cut it like that, what shape do I get? In there I get a circle. See that? When that plane cuts through. Or here, if my plane cuts through right there, what shape do I get? Well, it's a 5-sided shape, so that would be a pentagon. That's my cross section. If I take a slicer and I slice through like this, through a cylinder, what is the shape of my cross section there? Well, that would be a rectangle. And again, this is looking at it at kind of a strange angle, but that should be a rectangle, assuming this is a true cylinder. What's the cross section here? Well, there's the cut. Looks like a rectangle to me. I'm going to go with that for my cross section. This one is wider on the top when it cuts through this object and thinner on the bottom, but it looks like these two lines are parallel. So this is a four-sided shape with one pair of parallel opposing sides. That is called a trapezoid. And then finally, here's my slicer right there. It cuts the corner off of this shape, this prism, and it creates a triangle. The last three, here's my slicer that plane slices through this pyramid, and the cross section is the same shape as the base, which is a rectangle. I can tell that because this side matches that side and this side matches that side. So not all four sides are the same, but the angles in the corners are 90 degrees, so that would be a rectangle, assuming that the sliced through section is parallel to the base. So I'm going to call that a rectangle. Here's my slicer. It slices it exactly in half this way, and that looks like a pentagon, my cross section. And then finally, this little slicer slices just the corner off of this box shape, and then that three-dimensional object there would be a long, thin triangle.